In this unit, we're going to discuss two systems analysis and design topics. We're going to discuss databases and security. And these topics that we discuss in this unit are valid for whether you're taking a structured systems analysis and design course or an object-oriented systems analysis and design course. So they would apply equally to both, and you would see a similar unit in either of those classes. So first, we're going to talk about databases, and I'm not going to talk too much about database design here. We're mostly going to be talking about how databases work and some considerations when you're doing database design. Depending on which database you've chosen for your project, whether as far as type, whether it's a relational database management system or an object-oriented database management system, or a database management system that doesn't even do relationships or object if there's some need to do it that way. Just what the concerns and things that you would do. And if you do take those, whichever one of those database engines you go with, even the specific engines will certainly guide your actual database design. And certainly a course that you might take on databases would expand on database design. You could take whole classes that talk about how to do database design and to be a DBA and things like that. So we're going to talk about databases and database management systems and why they're important in modern information systems. Most modern information systems have some kind of a database. Almost all of them, I would say, use one of the major deep database engines like Oracle, MySQL, or Microsoft SQL Server, something along those lines. Database design transforms the domain model class diagram into a detailed database model for the system. So usually we take our domain model class diagram, which we did in the analysis phase, and that feeds into some kind of a detailed database model for the system. And sometimes a system analyst will do that design, and sometimes that design is done by the DBAs. So it could go either way. As a systems analyst, you certainly do have to be fluent in database design. A database management system is used to implement and interact with the database. So you'll have some kind of database management system, and like I said, they could be Oracle, Microsoft SQL Server, MySQL are the big ones. Certainly there are many others. After we talk about databases, we're going to talk about controls and security. So we'll talk about system controls and security, which are crucial issues to databases and also apply to other aspects of the system. So we'll talk about it in relation to the databases and with other parts of the system. So first, let's cover some basics about databases. First, a database. It's an integrated collection of stored data that is centrally managed and controlled. So a database management system is a system software component that manages and controls one or more databases. Physical data store is the database component that stores the raw bits and bytes of data. So most database engines store some kind of a file, some raw file that contains the data. In order to use that data that's in that raw file, you have to use the database management system. You can't just go and open that file. You have to have a database management system that interprets that file. So a schema is the database component that contains the descriptive information about the data stored in the physical data store. So almost every database management system has a way to define the schema of the database. In other words, the tables, the columns, the keys, the indexes, all that metadata that describes the data. So a database schema, let's talk about that first. An organization of individual stored data items into higher level groups such as tables. So usually in a database schema, we talk about tables, or in some cases, people call them relations. Associations among tables or classes. So those are also stored in the database schema. In other words, the database schema knows how different tables are related to each other, so it knows the ramifications, say, for deleting data in one table that references data in a different table. It stores the schema contains details of physical data store organization, including the types, lengths, locations, and indexing of data items. In other words, in the database schema, you not only define your tables and the columns, but you tell it what types of data can go in those columns. So can it be string? Does it have to be integers, Boolean, blobs, and so forth and so on? All the stuff that we define in a database for as far as data types go. A database schema can also talk about access and content controls, including allowable values for specific data items, value dependencies among multiple data items, and lists of users allowed to read or update data items. And if you work with any database management system, you will see all of these components that can be defined for your database schema. So you'll have to set up your tables, you'll have to configure the columns, what types of data can go in those columns, and any constraints about data within those columns, which would be your allowable values for specific data items. So some database management system components. So most database management systems, which I'm representing here by this big box, are so basically who interacts with the database management system. You've got three basic things that would interact with the DBMS. You've got the applications, which we're designing and developing in systems analysis and design. They would interact with the DBMS. Then you have users that interact with the DBMS, and you have database administrators, which would interact with the DBMS. And each one of those does things a little bit differently. So applications would interact with the DBMS usually using some kind of application programming interface or an API. We've talked about APIs before. Most of the major database engines have specific APIs, that there are well-developed libraries that you can use in your applications for connecting and using those databases. So, for example, Oracle, Microsoft, and MySQL all have the basic instructions for using APIs that for just about any language, C++ or Java or PHP or Python or any of these languages you might use when you're developing a system for the major database. Now there are some smaller database engines, so some more obscure ones, things like Sybase, or even some of these object-oriented database engines that maybe it's a little bit harder to find some of those interfaces that you can use to connect to the database. So certainly something you want to make sure is that there is a reliable method for your system to interact with the database management system before you choose a database management system. Users would access the database management system usually through a query processor. Each different database engine has its own query processor. For example, Microsoft SQL Server has the Management Studio Express. Oracle has something similar. MySQL has something similar. I think something like the Workbench in MySQL or PHP MyAdmin or something like that. And then you have database admins who would interface with the DBMS through some kind of an admin interface. So they would be defining the schema. They would be, which we just talked about, so they'd be setting up the tables and the keys and all that sort of thing. They would be setting up user accounts, passwords, policies, all that stuff would be through the database admin. So every database management system has sort of these three categories of ways people interact with the database management system. And then all three of those, whichever method is used to connect to the database management system, there's some kind of a core, in whichever database management system you use, there's some kind of core process that's the actual database engine. So that's the database access and control logic. So some common thread in the database management system which interacts with the physical data store. So all of them have some physical file that stores the data that's being stored in a database, and that's accessed through the database access and control logic. So every database engine pretty much has this basic structure. Of course, this is a very simplified explanation of it. So you could dig into this a lot deeper with each of the major database engines, but we don't really cover that too much in this class. You can take certainly other courses about databases and learn about that sort of thing. So by and large, most of the databases that we use for systems, for large enterprise systems, are usually going to be relational databases for a variety of reasons. A relational database management system organizes data in tables, or what we call relations. So in a relational database, another term you could use is relations. Most people don't use that term, but that's the technical term for tables in a relational database, a relation. A table is a two-dimensional data structure of columns and rows. I think most of us are familiar with that concept of columns and rows. You open up a Microsoft Excel spreadsheet, you've got columns and rows, same thing in a database table. It's the same idea. A row is one horizontal group of data attribute values. An attribute is one vertical group of data attribute values. Again, I don't think I need to expand too much on what tables, rows, and attributes, aka columns. So column would be another name for an attribute. But these are the technical terms that you have to be familiar with. An attribute value is the value held in a single cell in the table. So just like in Microsoft Excel, that single cell would be the attribute value. A key is an attribute or a set of attributes, the values of which occur only once in all of the rows in the table. So anything that is unique to a row or to a record, we could say. So anything unique to a record, any value or any attribute that's unique to a record is the key. So a key has to be unique. That's the important distinction there. Keys don't have to always just be one value. It could be a combination of different values to get a key. And that certainly does happen naturally in some databases. The primary key is the key chosen by the database designer to represent relationships among rows in different tables. So usually the primary key is what could be referenced by other tables. So you have a key, and then you have a primary key. A foreign key is an attribute that duplicates the primary key of a different or foreign table. So a foreign key is a column in a table that references the primary key in another table. And I think I've got a graphic here that kind of shows you that. So here's a graphic where we see the field or attribute names across the top. And by the way, this is from Microsoft Access. So if you have Microsoft Access on your computer, you can open up the Northwind sample database, and you can see this. So we've got the field or attribute names across the top. You can see they pointed out one row. The tuple, by the way, is the computer science technical term for a row in a database. Is called a tuple. You'll learn about that in a database class, or record. So you can use the term row, tuple, or record. Very few people use the term tuple. By and large, most people use the term row or record to refer to that. And in the middle, the green circle, the big green circle, we've got where it shows a field, and there's a specific field. If you look there, we've got one row or tuple, and where it intersects with the green circle, that's the specific attribute that describes that row. In this case, it's casual chino trousers, whatever that is. And then we have the blue circle kind of on the lower left there. That's showing you one field or attribute value, and that would probably be the primary key in this database. The product item ID would naturally be the primary key for that table. So here's an example of, you can see the primary key for product item on the upper left-hand side, which is circled in red, and it's referenced in inventory item. So in inventory item, there's a foreign key, which is the second column. So product ID is the foreign key, which references the primary key from product item. So for example, for inventory ID, for all of those inventory items, so all of the items that you see in that table at the bottom, they are all different types of casual chino trousers because it points to that foreign key. So these appear to be different sizes and colors of these particular trousers. So there's a lot of records in there, obviously, because pants can come in lots of different sizes and colors. For every size, you need all those different colors. But that's an example of a foreign key relationship. So when you're designing a relational database, so first of all, we're probably going to start with the domain class model the domain class diagram, which we talked about in the analysis portion of the course. Now, the reason you would not use the class diagram from your design is typically your design class diagrams have a lot more classes that we don't care about in the database. Remember, everything that we brainstormed in the analysis phase is all things that usually we have to track in our system. We're not really thinking about all of the infrastructure around that stuff that we have, all the core domain problems that we have to solve. So when we're designing our database, there's a lot of noise, a lot of clutter in our design class diagram, but in our analysis phase, when we did our domain class diagram, that has basically what we need in the database. And it's very basic. We've got our attributes, and we've got the names or the classes that we have to. So a lot of students struggle with that sometimes. What's the difference between a database diagram and a class diagram? They all seem to be very similar, but obviously a database diagram is quite different from a class diagram. But a design class diagram does not manifest itself as a database diagram, whereas a domain class diagram would manifest itself as a database design diagram. So I just want to kind of make that clear how that works. So first, we create a table for each class from our domain model, our domain class diagram. And we're going to choose a primary key for each table. And if we don't have anything appropriate to use as a primary key, we have to invent one. So for example, you might have a student, one of your classes could be student, but there's nothing that uniquely identifies the student. Sure, they've got a phone number, but that could be, what if you got siblings or something like that, so that you can't use that. Yes, they have a name, but different people could have different names. For example, my name is Brian Green, and there are lots of other Brian Greens in the world. In fact, if you said, somebody who's a college teacher named Brian Green, that would limit it to probably 20 different Brian Greens. So even that doesn't limit it. So sometimes you have to invent a primary key. So in that case, we could say student ID. We could just create a student ID. And most systems do this. Some database designers, just as something that they always do is create their own private or primary key, and they just make it some kind of identifier that gets created in the database. Different database engines allow you to do that in different ways. Then we're going to add foreign keys to represent our association. So in our class diagram, we probably showed these associations, that a student can be in many classes and a class can have many students. And then we have enrollment that was in between that as to, to sort of connect those two together, that we, because when we looked at the rules, we know that we can't have certain types of relationships. So we would look at those relationships and we make sure that our foreign keys either reflect or enforce those relationships. So we have to create new tables to represent many-to-many. So in that example that I just gave you, we've got students and classes. We would need some new relation to represent that. So we can't have multiple foreign keys in both tables. So we would probably have something like enrollment that would show the student ID and the course ID. And of course, both of them could appear many times. We sort of looked at that earlier in our class diagrams. I kind of showed you a little bit about how to do that. We would represent classification hierarchies, define referential integrity constraints, meaning that maybe you can't delete a student if they're currently enrolled in a class. That would be a referential integrity constraint, because you don't want to, if the student's deleted but they're enrolled in a class, then, there could be some issues downstream. So those types of rules would have to be enforced in your database. And then you're going to evaluate the schema quality and make necessary improvements. So that'd be things like normalization, which we'll talk about a little bit. And to choose appropriate data types based on that class diagram. So in that class diagram, the different attributes, you'll have to figure out, is it an nvarchar, a varchar, or is it an integer, a double, a decimal, blob, what type of field is it in the database? And different database engines have different field types that are appropriate for different things. So you certainly would have to have some familiarity with the database engine that you've chosen as you create those data types. You would incorporate integrity and security controls. So finally, let's take a look at this process. So here we have a whole bunch of tables and attributes, and this is derived from our class diagram from the analysis phase. So this is from the RMO case study we've been looking at in all of these different presentations. On the left, we've got the tables. The tables are basically the classes from that class diagram. And on the right are all the attributes. So this would be the first thing we would take a look at. So first we would have, you would just put this all into a table. Then we would say, okay, for each one of these tables, is there some primary key that we can use? So here's the next version. You can see for the accessory package, we created accessory package ID. And for cart item, we created cart item ID. For customer, we have the account number, which is a good natural key. Inventory item, we created the inventory item ID as the key. And these keys don't necessarily exist in the class diagram that we did. They weren't needed in that class diagram. But in a database diagram, we have to have these primary keys, so we create those. The next thing we do is, based on that class diagram, we fill in the foreign keys. So each one of these tables, we have to put the foreign keys. So take a look at this. Now, by the way, in bold are the primary keys, and italicized are the foreign keys. So you can see cart item as an example. It references the inventory item, and it references the online cart. Let's see another example. So inventory item references product item ID. So every inventory item has a product item ID that it references. The online cart table references the customer account number. So every online cart has to be associated to a customer or some kind of customer account number. So before it can get created in the database. Now, maybe while a customer is building their cart on the web page, at that point it's not in the database. But once it gets in the database, it has to have a customer account number. So that would enforce that business rule. So designing relational databases, we talk about referential integrity, a consistent state among foreign key and primary key values. So referential integrity means that, that we don't have, you always have to have a valid foreign key if you have a foreign key. Referential integrity constraint, a constraint stored in the schema that the DBMS uses to automatically enforce referential integrity. High-quality relational database schema has these features. Flexibility, or ease of implementing future data model changes. So we can add columns later on. We can change data types, things like that. Lack of redundant data, which we normally achieve through normalization, which you would learn in more detail in a database class, but normalization is a formal technique for evaluating and improving the quality of a relational database schema. So let's talk more about database normalization. The term first normal form, we're usually talking about restriction that all rows of a table must contain the same number of columns. So we can't have, so for example, if you had online cart, different carts could have different numbers of items in them. And on your first run through your database design, you might have variable numbers of columns based on how many items are in the cart. Well, we can't do that in a real database, so we have to fix that. We have to have a fixed number of columns. You can't just have any number of columns in most relational database systems. Now, object-oriented databases, you can do that, and some of those are a little bit more flexible, but we're going to focus on relational because that's by and large what's used in most systems. So you can't have repeating groups of attributes. Functional dependency is a one-to-one association between the values of two attributes. So attribute A is functionally dependent on attribute B if for each value of attribute B there is only one corresponding value of attribute A. The second normal form is a restriction that a table is in first normal form and that each non-key attribute is functionally dependent on the entire primary key. So we don't have multiple attributes. So every attribute in the table is functionally dependent. So in other words, if you had an address, for example, the address in a customer table, so you got a customer table, and in that customer table you have an address. Well, is the address functionally dependent on the primary key in that case? Well, I would argue that it's not, because you could have 3 customers with the same address, as an example. Or you could have one customer with 3 addresses. So it's not really functionally dependent, so we would move that stuff into its own table and then create new keys, like maybe address ID and a foreign key to the customer ID to get the second normal form. And finally, third normal form is a restriction that a table is in second normal form and that no non-key attribute is functionally dependent on any other non-key attribute. Now, I should mention about, for this course, understanding normalization is not as critical as if you were in a database course. But one thing I do want to make clear is that when you're doing design for databases, in some cases, we obviously want to get the third normal form, but in many cases, we go back to second normal form for performance reasons. So you'll find in the real world that sometimes that does happen. As a designer, it's important to know that because we can't always demand that that our databases be in third normal form. Sometimes there are reasons to back down for certain tables and in certain cases to second normal form. All right, so data access classes. So once we create our database, part of the design, part of our design tasks is going to be creating these data access classes, which we already talked about in the previous unit. So I talked about adding these data access classes. In this case, we've got the promotion object or the promotion class on the left-hand side, and the promotion class has a corresponding promotion data access class, which handles connecting to the database and inserting those records and selecting those records. And you can see a little bit of a snippet of code there. So what they're showing you here in the textbook is that the class interacts with the domain class interacts with the data access class on the right-hand side, and that's what interacts with the database management system. Typically, you wouldn't want the promotion class connecting directly to the database management system, because then we would have to have SQL logic, our actual code for using that API I talked about for the DBMS within that promotion class, and that would give us very low cohesion and tight coupling, which we don't want. We want the opposite, which we talked about previously. And you can see even there's a little snippet of code there of some stuff that you might find in that promotion data access class. In many cases, when we're developing an enterprise system, having a single database server is not going to be feasible for a variety of reasons. So a single database server architecture, one or more databases are hosted by a single database management system running on a single server. A replicated database server architecture is a complete database copies are hosted by cooperating database management systems running on multiple servers. A partitioned database server architecture is multiple distributed database servers are used and the database schema is partitioned. So different servers have different parts of the database, which is appropriate in some cases. The reason we're talking about this in this unit is that in some cases, you need high availability of the data that's in these databases. So you don't want to have it in just one place where it could go down. So for a variety of reasons, we have to have different copies of the data, and we don't want to have just a single point of failure. So when you're developing a system, it's a good idea to decide, do we have a single database server architecture or some kind of distributed database architecture? And for distributed database architecture, our two options really are replicated and partitioned for within our organization, or you can use cloud-based database server architecture, which is using some kind of cloud computing service provider to provide the database services. So something like Amazon could do that. So here's just a little image to show you the concept of a distributed, a partitioned distributed database architecture, where different parts might be in different places. And here's an example of a distributed architecture where, perhaps our warehouse has one replicated database partition, and our retail store might have different replicated partition, and our phone center has a different replicated partition. And then there's some kind of central database server that ties all that together. And different database management systems support this in different ways. All right, so we've talked about the database portion. Now we're going to talk about the need for controls. We're going to talk about integrity controls and security controls. So our book talks about a couple different scenarios. So for example, a furniture store sells merchandise on credit with internal financing. Salespeople sometimes sell furniture on credit to friends and relatives, but how do we ensure that only authorized employees can extend credit and record payments and adjustments to credit accounts? So I can't just give credit to, my cousin John that comes in to get a couch and, he's got a credit score of 420. How do we prevent him from getting credit, just because he's a friend of somebody's? Another example, a bookkeeper uses accounting software to generate electronic payments to suppliers. So how does the system ensure that the payment is for goods or services that we actually received? Or how does the system ensure that no one can generate payments to bogus suppliers? So what's to stop the accountant or the bookkeeper from just writing checks to anybody they want? They've got all the checks there sitting on their desk. Why can't they just write themselves a check for $100,000? So your system has to somehow keep that kind of thing from happening, and you have to design controls to keep that from happening. Another example, an online retailer collects and stores credit card and other information about customers. How does the company ensure that customer data is protected and secure? So designing system controls. Controls are mechanisms and procedures that are built into a system to safeguard the system and the information within it. An integrity control is a control that rejects invalid data inputs and prevents unauthorized data outputs and protects data in programs against accidental and malicious tampering. In other words, an integrity control prevents people from putting invalid data into the system, and it also protects people from seeing information that they shouldn't see. Security controls are part of the operating system and the network and tend to be less application specific. So integrity controls are application specific, security controls a little less so. There is some overlap between integrity and security controls, and this is from the textbook that we're using this semester, which shows basically some of these different controls that we're going to talk about. So integrity controls, we have input controls. Is a control that prevents invalid or erroneous data from entering the system. So a value limit control, a control that checks numeric data input to ensure that the value is reasonable. For example, if you have an employee system and you're putting in the salary, maybe somebody misinterprets the hourly salary to be yearly salary and puts 100,000 in there. Well, it's pretty unlikely that somebody's earning a hourly salary of $100,000. So you could have some kind of control that does a sanity check on that data. A completeness control is a control that ensures that all required data values describing an object or transaction are present. A data validation control is a control that ensures that numeric fields that contain codes or identifiers are correct. And a field combination control is a control that reviews combinations of data inputs to ensure that the correct data are entered. So some additional integrity controls would be things such as access controls, a control that restricts which person or program can add, modify, or view information. So who can do what with the system. A transaction logging is a technique which by any update to the database is logged with audit information, such as the user ID, date, time, input data, and type of update. So somebody could go and audit that later on. So if you wanted to find out, who made a change to the salary of a certain employee, you'd be able to find that information out. So transaction logging is pretty important. Complex update control, a control that prevents errors that can occur when multiple programs try to update the same data at the same time, or recording a single transaction requires multiple related database updates. Most database management systems do this inherently. So Most of them automatically do this in the back end, although sometimes you can code around that a little bit with some database management systems for performance reasons, but it's important to understand what kind of complex update control you need. Output control is a control that ensures that output arrives at the proper destination and is accurate, current, and complete. Sounds simple, but again, most database engines do this inherently, at least the part about being accurate, current, and complete. But again, there are ways that you can work around that for performance reasons. So it's important to know how accurate does the output have to be. If you're a bank and it's an output that shows, the customer's account details, that probably has to be pretty accurate. But if you're Facebook and you're showing people's posts on Facebook, that probably does not need to be as accurate. So you can sacrifice some performance in that case for accuracy. So integrity controls for redundancy, backup, and recovery, designed to protect data from hardware failure and catastrophes. Redundancy is continuous access to data through redundant database servers and sites. So redundancy is not recovery from backup. Redundancy is all about business continuity. Backup is procedures that make partial or full copies of a database to removable storage media, such as magnetic tape or to data storage devices or servers at another site. And recovery is the procedure to read the off-site copies and replicate their content to the database server that can provide access to programs and users. So backup and recovery is all about disaster recovery. So for some reason you lose your online database that's running in some redundant environment, you've got a way to get back online. So preventing fraud. The fraud triangle is a model of fraud that states that opportunity, motivation, and rationalization must exist for a fraud to occur. So opportunity is the ability of a person to take actions that perpetuate a fraud. So for example, unrestricted access to all functions of an accounts payable system would enable an employee to create false payments or to cut checks to people without any authorization. So that would be an example of opportunity. So the first part of the triangle is the person has the ability to do something they're not supposed to do. But second is the motivation or a desire or need for the results of the fraud. So if you got somebody who works in accounts payable that needs the money, they need the money and they have the ability to get that money by making a false payment. And then third, usually, unless the person is completely devoid of morals, they'll have some rationalization, excuse for committing the fraud, or an intention to undo the fraud in the future. So, for example, an employee might falsify financial reports to stave off bankruptcy, thus enabling fellow workers to keep their jobs. So maybe their heart was in the right place, but that's still a fraud. So factors affecting fraud risk, we have separation of duties. So in other words, separation of duties is a way to reduce fraud by giving, so in other words, you can't cut a check until somebody else approves it. So two people have to sign off on something like that. Records and audit trails, so everybody knows they're being watched. Same with monitoring, asset control and reconciliation, and then finally security. So you can certainly take a look at these and pause the video and take a look at the different techniques we have for reducing the risk of fraud. So designing security controls. We're almost done. So designing security controls. Security control is a control that protects the assets of an organization from threats, with a primary focus on external threats. So usually we're worried about threats from the outside. Although to be fair, security threats from the inside are also pretty common. But we've handled, hopefully, most of those with integrity controls. So when we talked about integrity controls, that was mostly about threats from the inside. Now we're talking about threats from the outside or external. We have two objectives: maintain a stable, functioning operating environment for users and application systems, 24 hours a day, 7 days a week if it's an enterprise system. So if you take an IT security class, they'll talk about CIA, which is confidentiality, integrity, and availability is what the A stands for. So usually when we talk about IT security, we also are talking about availability, which is an important part of the triad of IT security, the CIA. So firewalls are meant to protect from hackers, viruses, denial of service attacks, and things like that. We also want to protect information and transactions during transmissions across the internet and other insecure environments. So information could be intercepted, destroyed, or modified. So access controls. One way is authentication. Authentication is the process of identifying users who request access to sensitive resources, while authorization, which is a little different, is the process of allowing or restricting a specific authenticated user's access to specific resources. So to put this in other terms, Authentication is who you are, and authorization is what are they allowed to do. So we want to make sure we have that baked into our system. Multi-factor authentication is identifying who somebody is using multiple methods. So instead of just asking who are you and taking their word for it, we might also ask them for a password and maybe something they have like a key fob, or there's or maybe a retina scan or a fingerprint scan or something like that. So some other method of identifying who they are. An unauthorized user is a person who isn't allowed access to any part or functions of the system, whereas a registered user is a person who is authorized to access. So usually we want to protect ourselves from those unauthorized users. A privileged user is a person who has access to the source code, executable program, and database structure of the system. So these are our system administrators typically. So encryption, one way to protect our data is through encryption. Some common types of encryption or some common types of data requiring protection are financial information, credit card numbers, bank accounts, payroll information, healthcare information, and other personal data. Strategies and plans for products and other mission-critical data, so anything that's intellectual property, for example, government and sensitive military information, data stored on portable devices such as laptops and cell phones. So if people are going to be using the system from their laptops or cell phones and they might have sensitive data on those devices, it's important to make sure it's protected. So how do we encrypt? Encryption is the process of altering data so unauthorized users can't view them. So decryption is the process of converting the encrypted data or scrambled data back to their original state. I think most of you are probably familiar with these concepts. We do that with an encryption algorithm. It's a complex mathematical transformation that encrypts or decrypts binary data. Usually we have to use an encryption key, which is a binary input to the encryption algorithm, usually a long string of bits, hopefully a very long string of bits to make it more secure. There are two types of encryption. We have symmetric key encryption, which is an encryption method that uses the same key to encrypt and decrypt the data, which is relatively simple. So there's an example of symmetric key encryption, where both sides use the same key. We use one key to encrypt the data and the same key to unencrypt the data, but that requires that person 1 and person 2 share that key ahead of time. They both have to have that key. Public key encryption, which is asymmetric encryption, is where we use one key to encrypt the data and a different key to unencrypt the data. Usually you have what's called a private key, which can unencrypt the data. You keep that for yourself. You don't give that to anybody, but you give everybody else your public key. Anybody can encrypt your data with the public key, but only you can unencrypt it with the private key. So it doesn't matter who gets that data downstream. No one will be able to unencrypt it except for you. So those are the two options we have. Secure sockets layer and the transport layer, or TLS, transport layer security. These are two encryption standards that we have available to us on the internet for creating these virtual private networks, which we talk about. IPsec, by the way, is another one. That's usually what we use for VPNs or virtual private networks. So your book talks about these in a bit more detail. And then HTTPS is using SSL or TLS over HTTP. So if you develop a system that's web-enabled over the internet, encryption is sort of baked in for us already if we're using HTTPS, and we can design for that. All right, so we've talked about databases and security controls. I'm just going to show you here the summary of everything that we've discussed, and you can pause here and take a look at those if you like, and if you have any questions or concerns, let me know, and thank you for watching the video.